Hello and welcome back again to this online course on fundamentals of composites and cellular materials. So, for the past few classes, I was discussing about initially I started talking about composites, their basics, then I talked about fibers. For a long time I discussed about synthesis techniques of different composite materials like polymer matrix composite, ceramic matrix composite, metallic matrix composites, and then we started talking about interface, the importance of interface, how do we control or engineer the interface in composite material, what is the role of interface in composite materials. Different kind of composite materials have different kind of interfaces. So, in details we discussed those aspects. Okay. Now, let us go into a new topic which is mechanics of composite materials. Okay. So, in today's class and the next few classes we will discuss about the mechanics of composite materials. We will try to learn, we will try to understand the mechanics of composite materials. So, in today's class I will talk about the basics of mechanics, and then we will start talking about unidirectional lamina. So, I will explain all these terms as we move along. So, now what we are actually trying to do, so what we understand that composite materials could be a matrix, and then we have reinforcement like this, could be like particles, right, or we can have composite materials where we can have fibers. Now, when we are talking about fibers, fibers could be continuously aligned like this, okay, where load could be applied in longitudinal direction, okay, or load could be applied also in the transverse direction like this. Again, we can have composite materials reinforced with fibers only, but in this case the fibers may not be continuous, but short fibers, and when we have short fibers, those could be aligned like this, or we can have short fibers in a composite material which could be randomly distributed like this. And then we can have this kind of one set, let us say this is one set. So, we can have this set as a 3-dimensional plate where all the fibers are distributed like this. You can see here, okay, which we are calling as, so this one we are calling as lamina, and we can have multiple lamina being arranged in different orientations. Okay. So, we can have all these combinations. Okay. You can see we can have all these combinations. Now, we intrinsically know the properties of the matrix and the fiber or the particles. The mechanical properties like yield strength, UTS, Young's modulus, Poisson's ratio, this we know of the constituent materials, but how once we make these different combinations, what kind of property ultimately we will get in the composite material, that we do not know. Okay. So, we need to know that, we need to know how to calculate the overall properties once we mix and match different combinations of matrix and reinforcement, and we can have different orientations, we can have different kind of fibers, orientations, short fibers, long fibers, continuous, random, we can have multiple lamina, okay, and then how do you get the different properties. So, in next few classes starting from today, the aim is would be to get the overall properties, mechanical properties of composite material, and that is why we need to learn mechanics of composites. Okay. Now, mechanics could be studied in two levels. One is we are calling it as micromechanics, other one is macromechanics. Now, micromechanics means, this is micromechanics. Okay. That means microscopically, there will be change or inhomogeneity, and that inhomogeneity, how do you take account those inhomogeneities ultimately in the overall properties. So, you can see, if we talk about a single lamina, we are talking about micromechanics. Okay. And then we have multiple laminas here stacked together, we are calling it macromechanics. Okay. So, we will start with micromechanics, then we will move to macromechanics depending upon how much time we have. Let us discuss about mechanics of composites. And I already discussed about different combinations. For example, we can have particles being distributed. Similarly, we can have continuous aligned fiber, and we can have different kind of loading directions like longitudinal. This is longitudinal, and we can have transverse. Okay. Similarly, we can have short fibers which are aligned, and also we can have we can actually have this kind of short fibers which are randomly distributed, and then you can have stack of lamina. Okay. And our aim would be to understand the overall mechanical properties of these combinations. Okay. So, before we start, initially we will be having some assumptions, some basic assumptions we will have as we move along. What are those basic assumptions? The first assumption would be that the composite material which I am dealing with does not have any porosity. Later we will incorporate porosity as a third phase, but initially for our initial calculations, let us consider that there is no porosity in the composite material, or it is 100% densified. Okay. The second point, again an important point, is that uniform distribution of reinforcements. Okay. That means the reinforcement is distributed homogeneously in the matrix. Okay. There is no inhomogeneous distribution, there is no agglomeration. Okay. Third point which we consider or which we assume is that no delamination, and I will explain what do I mean by that. No delamination. That means the interfacial bond is strong. Whatever load I am applying, there will be matrix failure or fiber failure, but initially we will consider that there is no interfacial failure or interfacial fracture or delamination. Okay. So, we can call it as interfacial failure. Okay. Fourth point, again a very important point, is that the load, again we are talking about initial assumptions, the load which is being applied either perpendicular or parallel to the fiber orientation. Okay. And then fifth point is that So, we talked about no porosity, we have uniform distribution, okay, no delamination, the load is perpendicular or parallel to the fiber orientation, or basically it will be longitudinal loading or transverse loading. These two only we will consider initially. Okay. Fifth point is no residual stress. We have talked about residual stress. During processing of composite material, because of difference in coefficient of thermal expansion, there will be always some residual stress at the interface, but we are considering, to make our life easier, initially we are considering there is no residual stress. And sixth point, okay, is that both matrix and reinforcement are linearly elastic. That is a big assumption, linearly elastic. Okay. That means, let us say we are trying to draw the stress strain graph, okay, and if you are trying to, let us say we have a metallic material, ductile material. So, how it looks like? It will be something like this. So, there will be a yield point, okay, and then there will be a plastic deformation and then fracture, something like this. Okay. But here we are considering only that the materials, both matrix and reinforcement, are linearly elastic. That means, basically it will not be having any plastic zone like this. It will be linearly elastic, be it matrix, be it reinforcement, does not matter, both are linearly elastic. So, with these assumptions, now let us move into our calculations. Okay. So, the first one which I would like to discuss is that this combination. So, case 1, okay, and we are talking about continuous fiber aligned like this, and we are applying longitudinal loading. So, how is the composite material? It is reinforced with continuous fiber aligned, and the loading is longitudinal loading. Okay. So, now let us look into that. So, let us see how it, let us try to draw the stress strain graph. Okay. So, this is, let us say your strain and stress, and let us consider that this is our fiber material with a very high fracture strength, and then let us consider this is the matrix material with higher amount of ductility. Okay. So, this one here, this is sigma f u, that means sigma of the UTS of the fiber, ultimate UTS. Okay. So, this is the UTS value. Okay. Similarly, this one is sigma matrix ultimate. Okay. Again we can have the strain value. So, this will be epsilon fiber ultimate, and for matrix it will be epsilon matrix ultimate, epsilon mu. Okay. So, I will come back here again, let us look at here. So, now if we have this kind of composite material where we are applying a load in longitudinal direction, okay, and what was one assumption you remember, that there is no delamination, right, no delamination. So, in this case this epsilon c, c means composite, okay, epsilon c would be equals to epsilon m equals to epsilon f. Why is that? Because there is no debonding. So, if you apply load, if there is strain in the composite material, the matrix and the fiber both will be experiencing similar amount of straining, is not it? And this condition is called isostrain condition. Strain of the matrix, the fiber and obviously the composite material are equal, isostrain condition. Okay. Now, if you look at the stress values, so sigma f is how much, is equals to epsilon f multiplied by E f and sigma m is equals to how much, epsilon m multiplied by E m. Now, the value of E f and E m are similar, same values, right. So, from these two cases we can see that E f is always higher than E m, no doubt about that the modulus of fiber, that is how we choose our materials, that generally the modulus of fibers is quite higher than the modulus of the matrix. Now, if you look at these two equations, we can see from here that sigma f is always higher than sigma m. It is a big thing. Okay. Sigma f is always higher than sigma m. That means, the stress being experienced by the reinforcement of the fiber is always higher than the stress being experienced by the matrix. Later we will see that the load being carried by fiber or the reinforcement is also quite higher than the load being carried by the matrix, and that is why the load transfer mechanism should be efficient. That is why the interface plays an important role, that the load should be transferred properly, because the maximum portion of the load, the maximum amount of the load would be carried by the reinforcement particles because of their higher modulus. Okay. All right. So, let us move on. Now, P f, let me use different color. P f, sorry, P c P c is equals to, so here you can see this P c is equals to what? The load being experienced by the matrix plus the load being experienced by the fiber, right. Now, what is P c? P c is sigma c multiplied by A c. A is the cross sectional area of the composite material. Okay. So, you can have like this kind of composite material. Okay. So, this is the A c. So, that is your A c. Okay. So, sigma c into A c equals to P m will be sigma m multiplied by A m plus sigma f multiplied by A f. Okay. If I divide the both sides by A c, that means sigma c is equals to sigma m into A m over A c plus sigma f into A f over A c. Now, what are these terms? A m over A c or A f over A c are V m and V f, volume fraction of the matrix and volume fraction of the fiber. Okay. So, you can write sigma c is equals to sigma m into V m plus sigma f into V f, or you also can write like this, sigma c is equals to sigma f into 1 sigma f into V f, sigma f multiplied by V f plus sigma m multiplied by 1 minus V f, because V m plus V f is equals to 1, V m plus V f is equals to 1. Okay. So, we get this one, all right. Okay. So, now if we can write like this. So, sigma c is what? Sigma c equals to, sigma is equals to how much? E multiplied by the strain. So, you can write from sigma c here E c multiplied by epsilon c is equals to sigma, you can write E f into epsilon c into V f plus E m multiplied by epsilon m into 1 minus V f. Obviously, this E m, E c and this is E f, sorry. So, all these terms are same. So, you can write from there E c is equals to E f V f plus E m 1 minus V f. So, you get this equation and you also get this equation. These two equations are called rule of mixture, rule of mixture, in short ROM, as you all understand. Okay. So, you can see, you can get the modulus of the composite material using this equation. Okay. Now, let us go to another thing. Let me go to the next page. Okay. Now, what we are trying to do here is that initially I mentioned that the load being carried by the fiber or the reinforcement is always higher than the matrix. Let us look into that. Okay. So, now what we are trying to find out, the ratio of load P r. Let us consider P r. P r is what? Is equals to load being experienced by the fiber over the total load of the composite material, P f over P c. Now, what is P f? Is sigma f into A f, and here sigma f A f plus sigma m A m. So, you can write this one as sigma f into V f over sigma f sigma f V f, sigma f V f plus sigma m V m. Okay. Now, that you can write like this as E f V f over E f V f plus E m V m, because you can actually divide that by the strain value and you can get E f. Okay. Now, let us consider E f over E m is equals to, let us say, E r. Okay. So, now we get what? P r is equals to, okay, and we divide it by EM. So, Vf over Vf plus Vm over ER, okay, isn't it? Right. Now, let us consider a case where we are considering that EF over EM, or basically EF is 10 times higher than EM. So, we can consider this as 10. Okay. In most of the polymer matrix composites, it is like that EF is way higher than EM, it is close to 10 or even higher than 10. Okay. And then let us consider we are actually adding around 0.2% volume fraction of fiber, or Vf is equals to 0.2 only. So, now you calculate PR value, PR is equals to 0.2 over 0.2 plus 0.2 over 10. So, you can calculate it and it will be seeing it will be coming around 70%. So, you can see that in this particular example 70% of the total load will be carried by the reinforcement itself. Okay. Now, obviously, there could be more or less based on what kind of elastic modulus ratio and how much amount of reinforcement particles or fibers are used, the volume fraction of that. But you can see here from this particular example that a good amount of load, total load would be actually carried by the reinforcement, and that is why again I reiterate the load transfer mechanism should be very efficient, and that is why I am too keen on the many times I was talking about that ultimately the interface should be of more importance. Okay. Now, let me show you this particular what we just discussed. Let us show that in the form of a graph. You can see in this particular case. Okay. So, you can see here we have EF over EM, okay, and then we have here PF over PC, okay, and you can see these lines are for these different lines are for the volume fraction of the fiber. Okay. So, from 0.2 to 0.3 to 0.5 there is increase in volume fraction, and these lines are following those trends. Okay. Now, you can see, let us just consider here, you can see let us say EF over EM is around 10. Okay. So, you can see here this, okay, sorry, just a second. Let me go to desktop. Yes. So, you can see here in this particular case when EF over EM is 10, and you can see around let us say 0.3 volume fraction is being used. So, you can see the load, how much the ratio of PF over PC is. So, because of the higher value of EF over EM, you can see that the amount of load being carried by the fiber is quite high. Okay. So, now let us discuss something else, is that let me go back to my whiteboard, okay, and let me go to the previous, okay, next page. Okay. So, we are here. Okay. Now, if we keep on applying the load, okay, in this particular scenario, then what if we try to draw the resultant of the composite material, how would that look like? Obviously, it will be in between somewhere, the slope will be, okay, like this will go, and how long it will go, how further will it go, how further will it extended? It will be going to a particular strain value which is equal to this epsilon Fu, because once there is failure in the fiber, okay, then composite will fail. Okay. So, then it will be able, because at that particular load, obviously, if the fiber has failed, then the matrix will not be able to withstand that high amount of load. So, there will be instantaneous matrix failure. Okay. Now, the point here is that what we want to understand. So, basically this is actually this one is sigma composite, and epsilon Fu is equals to your epsilon Cu as well. I hope you understand this point. Now, which we want to understand here is that if we want to find out how much volume fraction of fiber is enough to go beyond the matrix strength, okay, or let me go to another page and let us see what I am trying to say here is that we have sigma mu, which is basically the ultimate strength or UTS of the matrix material. Okay. If you remember this one, let me just draw it once more here, so that you remember it. This is the fiber, this is our, let me use another color, this is our matrix material. So, this is sigma Fu, similarly this is sigma mu, and this is our epsilon Fu, this one is epsilon mu, and then we have the composite material in between here. So, and the okay. So, it will be equal to this, and here is our epsilon sigma c, sigma Cu. Okay. Good. Now, what I am trying to say here is that how much volume fraction of fiber is required to say that it is effective reinforcement. Okay. Or in other way, we can say when sigma mu will surpass the value of the sigma mu at least will be equals to the value of sigma LTU. LTU means basically for the composite material longitudinal tensile ultimate. Okay. So, this is for the composite. So, that means you need certain amount of volume fraction for this one, or at least it will be either it will be sigma LTU will be equals to or more than sigma mu. So, let us try to find out that thing. Now, what is in this case if we try to find out, so sigma c is what from our earlier learning we know sigma f Vf plus sigma m 1 minus Vf, and that is true for at any point, any of these points, that is true. Now, once we reach this point, this particular point, okay, then we are calling it as sigma LTU, and what is the value of sigma LTU from this graph? You can say it will be sigma Fu, because now it will be F ultimate, okay, multiplied by Vf plus what is the value of sigma m at this point? At this point sigma m's value is here, it is not sigma mu, but it is sigma m dashed, this value, right. So, you write sigma m dashed into 1 minus Vf. Okay. So, from here and that is equals to what, as we discussed, equals to sigma mu. Okay. So, now you can calculate from here that so V f multiplied by sigma f u minus sigma m dash is equals to sigma m u negative sigma m dash. So, ultimately you get V f is equals to sigma m u minus sigma m dash over sigma f u negative sigma m dash. So, this V f is called V f critical. That means, this is the minimum amount of fiber required for, we can write like this, minimum amount of fiber required for effective reinforcement. Right. That means, the composite material should be at least reinforced with this volume fraction of fiber or reinforcement, to have higher tensile strength or higher UTS than the matrix, because that is the aim, that the aim is that to increase the UTS of the matrix beyond its own UTS. Okay. And this is the minimum amount of volume fraction of fiber which is required for effective reinforcement, as I was discussing earlier. Okay. And we will now move into some other aspects. We will talk about different kind of loading conditions, we will talk about different kind of fiber alignments and how to measure the mechanical properties in those cases, but we will discuss those things in the next class. So, today I will end my class at this point, and from here we will start in the next class. I wish you all the very best. Thank you.